Hi, my name's Nimish Lad. I'm a Vice Principal from Wren School in Northamptonshire. I'm here to do a video for Chat Physics on modelling to aid explanations. So when we talk about models, specifically in science education, we need to understand what we actually mean by the model and therefore how we're using it, what it's used for, and how we're going to use it to improve the student's understanding of an abstract subject area. A lot of the ideas in science are quite abstract and quite difficult for students to grasp mentally what's going on, especially where there's complex processes. So modelling helps students to understand that. So we're going to talk about when we should use them and why we should use them. And I'm going to go through an example of a model and potentially mention a couple of others that can be looked into. So when we're talking about models, like I mentioned, we're talking about ways to represent abstract ideas in a different way. So we could be talking about the idea of half-life in radioactivity, which is really tricky to grasp for many students. They struggle with the idea of radioactive decay taking place and varying over time. So there's different models that you could use to help explain that. And we use a mathematical model when we get to A level, where we talk about the idea of exponential decay to help understand that. But simple models involve using, say, a can of Guinness. And if you pour a pint of Guinness, you get a foam head on top of it, and the bubbles at the top pop. So the height of the head of Guinness sort of decreases over time, and the rate at which that decreases is directly proportional to how much of it there actually is, and that's the theory behind exponential decay. That's the theory behind also, sorry, it's the same process that happens within half-life. So there's useful ways in which models can describe abstract ideas, or at least represent abstract ideas. So we can use scale models when we're talking about size. So if a student's really struggling to get the idea of how small a nucleus is compared to the size of an atom, you could use a scale model to help understand that, in the sense of, how big would it be if the whole atom was the size of like a football field, or if the atom was the size of a city, how small would the nucleus be compared to that. We can use an analog or an analogy or representational models, and that's what I'm going to talk about today. So like the idea of Guinness is not actually half-life. It is not undergoing half-life, sorry, it is not undergoing radioactive decay. That isn't the exact process, but it's an analogy. There's a similar process taking place there. There's mathematical models. So like, again, going back to the idea of half-life, there's exponential decay that models the process of half-life, of radioactive decay. Also gravity. So gravity is a complex idea, and they've used the inverse square law, so 1 over r squared, to help explain in mathematically gravity, although we know that's not completely correct. It's a useful mathematical model to use. And then there's theoretical models, where we tie lots of ideas together to come up with a theory. So in the way that evolution first came about, where it brung together a range of different experiences, the model for that entire process was the process of evolution. So natural selection fed into that, as did other ideas, and that led to the idea of evolution. So we should be using models and explanations at very specific times. The way to think about it is a model is like, we are like doing something. It is like this. It is like that. It's not exactly the same. It is like this. So going back to the Guinness and half-life example, Guinness is not undergoing the process of radioactive decay. It is not therefore experiencing half-life. However, the process of the decrease in height of the head is like the process of half-life, is like the process of radioactive decay. So there's very much an analogy that can be drawn there. Scientists do this really often. It's part of the scientific process, but the model always comes after a scientific explanation when we're teaching. We can't have any chance for a misconception to crop in here. It has to be the scientific explanation and then a model used to help back that up, to really solidify that knowledge. That clarifies thinking. Quite often in exam questions, they'll draw on a model, or they'll use an analogy where they'll say, this is like this. How is this like this? How is a car, the example that I'm talk about in this video, how is a car going from a road onto a mud track back onto road like refraction? So after the scientific explanation is the best time to start talking about model, because what it does is it clarifies that they understand the science and can apply it to a model. So whenever I'm talking through a model with students, I try to get them to describe the model back to me in their own words, to see whether they're seeing the same things that I'm seeing. I go through ideas about, can they see the limitations of the model? Can they suggest any improvements to the model? And can they create and evaluate their own model as well? The whole idea of taking an idea and creating their own way of remembering it, but also looking for the limitations in it. A lot of these ideas, especially from this slide, are taken from a website called The Science Teacher, where they go through the entire process of modelling. So here's an example of a model. So we have a car. I'm going to try and draw onto this. Apologies if my drawings aren't particularly good. We have a car that's on a road. It then goes into mud and then back onto road. Now, as it goes on the road, it's going to be able to travel at a faster speed than it is in the mud. As it goes back from the mud onto the road again, it will go back to a faster speed. So in the mud, it'll be slower, and the road will be faster. The idea is that as this car hits this boundary, so this boundary here, so as this car from the left-hand side hits this boundary, one of the two wheels will hit the boundary first. So it'll be the bottom wheel. The bottom wheel will hit that boundary first. As it hits that boundary, it will be traveling slower than the top wheel. What that will cause is it will cause it to turn. So that's the crux of why refraction takes place, is why a beam of light changes direction, why in this situation the car changes direction. So if we break that down in terms of what's happening exactly on the boundary, that's the crucial part of this explanation. So where one wheel, the bottom wheel, hits the boundary first, it will start going slower as it goes into the mud. The top wheel will carry on going at the same speed because it will still be on the road. So you need to be able to, or we need to be able to describe that to a student in a different way as well. They'll get the fact that it's slower on the road slower in the mud than on the road. But how can we show that in a different way? Well, if you stood in front of the students and moved 1 foot slower than the other foot as you were walking, you turn in a circle. It's exactly the same thing that happens here. One wheel is going slower than the other wheel, and therefore it will start to turn. This is a model within a model there. We model the process of the turn taking place, the absolute crucial part of that explanation. And the same thing happens on the other side. So as the car goes along through the mud and then hits this boundary over here, that bottom wheel will hit ever so slightly sooner, and therefore we're faster, and it will cause a turn in the other direction. So the model here that we're using is a car going from road onto the mud and then back onto the road. I've been through this before I've been through the science. So right now, if we did it this way round to a student, this is a non-example of how to go about modelling. If we did it this way around to a student, they'd be thinking more about the road, the mud, and the car than actually light going between different mediums. This is why it's so crucial to go through the idea of the science first, and then as you go through the model, link in every part of what it actually is compared to the science. So if I just flick forward to the next slide, so I've just got to turn the ink off. That's the very straightforward idea of what's happening with refraction, where light comes in over here. So let's turn the ink back on. Where light comes in over here, it refracts and changes direction as it goes between each boundary. say from air to glass to air. Now, if I was to show that first and then say what is changes in direction happening at each of the boundaries, and then go back to that previous slide where we spoke about the car and the road, it would make so much more sense in the direction that I've just been through this explanation. This is why it's so important that we go through the science first before going through the model. The final thing I'd like to add to this is one of the bits that students struggle with is how to remember which direction it would bend in. So is it going to bend towards a normal at 90 degrees to the surface? It's probably easy to draw on this one. So if I was to draw a normal here, very badly drawn, you can see that over here, as it goes from air to glass on this boundary, the first boundary, it bends towards a normal. As it goes from glass back to air, it bends away from the normal. Well, the model helps to explain that, because if you think about the idea of two wheels, what that actually does is it spreads out the beam almost. So it helps to explain why it's going to bend one way and then why it will bend the other, because of the fact that each wheel hits at a different time. And that is one of the areas where this model really strengthens the student's understanding of how refraction takes place. So if you're interested in the idea of modelling, there's a few other physics-specific models that I like to use that I'll happily just go through now. I mentioned Guinness for half-life. It seems like I'm quite infatuated by Guinness now. I don't drink, actually. There's popcorn. That can also be used for half-life as well. They both have massive holes in the model. Okay, they both have massive holes in the model, and that's something to go into with students to help evaluate the model. This model has a hole in it as well. It only describes the wave nature of light. There's a particle nature of light as well, which this model can't explain, but the whole wave model itself falls down to try to explain certain ideas in physics. This talks about an idea of widening a beam. It's and giving it almost like a finite width. Waves don't exactly work in that sort of way, so this doesn't tie in that exact idea. But for explaining the idea of refraction and why things change direction, this model helps to solidify that knowledge of students. I hope you've enjoyed this video.